Okay, so last time we discussed that design needs to take into account implementation environment. Unlike analysis, which focuses purely on functional behavior without consideration for any implementation. So for example, here you need to design a file manager to encapsulate the differences between the difference of the underlying platform, the different OS APIs for file management, so that your applications can be easily portable. So this class here encapsulates the different OS calls. So we need to define many additional classes to deal with implementation environments in the design model. So we need to develop approaches for handling issues that have system-wide implications. So data management. So what data needs to be persistent? How is persistent data handled? You can use files, which is the easiest way of storing data. But the application has a burden of taking care of concurrency, concurrent access to files, locking, etc. by itself. So the application is very complex if you use files as the data management mechanism. But relational databases, DBMS, is better. The database takes care of a lot of the issues for you, so the application can be simpler. Object-oriented database management systems are closer to the application abstraction. So ODBs nowadays they're not very popular. They're not widely used. But I have used one before, where you can just write C++ classes and persistent and store them into the database as objects instead of converting them into tables as in a relational database. So I think this concept is a good idea, but it never caught on perhaps for more business issues than technical issues. Access control, that is who can access what. So if you have a registration system, the registrar can have write access to pretty much everything, while the student can have read access to the course catalog and course information, etc. And professor perhaps has write access to student marks. So each one has different access rights to different data, and how do you specify these access control policies? So one is the global access table, where you have on the horizontal access you have perhaps actors or login names. On the vertical access you have resource names, data names, where you can have a write or read as the table entry to specify who can access what. So that can be huge, because you may have many users and many resources. So access control list is more appropriate way, where you have each resource has a access control list that specifies who can access this resource and in what capacity, in read or write. So capability is another mechanism. So for specifying access control. So these are just different mechanisms for specifying the same information. They all have the same end result, but they have differences in efficiency in terms of time and memory consumption. Control flow. So how is processing initiated and controlled? If you have a sequential piece of software, not multi-threaded, single-threaded, then perhaps procedure-driven control flow. That is one procedure calls another one, which returns, and then it calls another one. So that's the traditional C or C++ programming for control flow. Or event-driven, where you have is especially suitable for all systems. So in object-oriented systems, we discussed objects as perhaps containing a finite state machine, responding to messages that come in and sending out messages as part of the state transition, right? So that's ideally suited for event-driven style, where events are passed between objects and trigger some actions, and so they form the control flow mechanism between the objects. So threads are yet another way where you have it's a concurrent variation of the procedure-driven control flow, where you have multiple threads. They communicate via shared data, protected by mutex mechanisms like semaphores and monitors, as you learned in the operating systems class. So it is harder to test and debug, as you learned in the OS class, because of all the race conditions, etc. But it's widely used. So for event-driven, you don't have global data, right? Event-driven, you just pass messages or events between objects. But for threads, you have a global data store and you're reading or writing with locks. So boundary conditions, including how our system initialized, start up, shut down, and failure and exceptions, how are they handled? So perhaps you need to have additional use cases for startup, shutdown, and recovery called administration use cases. So use cases, as in the requirements analysis stage, often only include the functional behavior. That is, register for a course. That's a use case. But you may have administration use cases like maintain a system, shut down, and repair some part of the system. So that perhaps can form a separate use case. So this is added at the design stage. And exception handling mechanisms for errors. So this is often provided by the programming language with the try-catch finally blocks for exception handling. So generic design mechanisms is a well-tried solution to a commonly occurring design requirement. That is, these are experiences summarized from many years of practitioner experience. So there are two types, two forms of design mechanisms. One is architecture style / design pattern. These two are different, but they're rather similar, so we group them together. So it's a named, well-understood solution to a common problem. In context, described in literary form. So literary form is this stylized natural language where you have a specific format for writing these design patterns. So it's really a blueprint for a solution, high-level description of a solution. So you need to read it and apply it to your system. So it helps novices to learn by example, to behave more like experts. So perhaps as a novice, we are designing a system. You never think of this way, but other people have done it, and you just borrow this experience from others. So you are learning by example. A style, architecture style, and pattern catalog documents particular styles and designs that are useful in a certain context. That is, the catalog describes the situation in which the style and pattern can arise and the solution for it. So you kind of can look up the catalog. You have a problem, you look it up, and if you find a solution corresponding to a problem, you just apply it. So we'll make it more concrete later. A framework is a reusable chunk of architecture. So it is a framework. It is a concrete solution. That is, it is code in the form of a library or a skeleton application in C++, in a concrete programming language. So it describes how a collection of objects work together to implement the structure part of several design patterns. That is, for example, Microsoft Foundation classes. That is, when you are writing a graphical user interface GUI application with Visual Studio, perhaps with Visual Basic or Visual C++, what you do is that you are using a framework provided by Microsoft. That is, what you're writing, for example, if you're writing a simple dialog box with a button click, and with the button click you bring up another message box, that application, what you write is perhaps just a few lines of code for the button click. But Microsoft provides you with hundreds of thousands of additional lines of code behind your back in the form of a framework. So you are using a framework, you only need to specialize a small part of the framework, and most of the generic classes are defined for you. So the framework defines generic classes that describe the collaborations between the objects that will be subclassed specialized when the framework is applied to a problem. So perhaps in the Microsoft framework, you have an abstract class called a dialog box, and you inherit from it, call it perhaps my dialog box, and then you add a button to it, add some event handler to it, and to specialize the generic dialog box. So the difference here, the framework is a concrete piece of software that you can use, you can extend. While the architecture style design patterns are abstract descriptions that you have to read and write code yourself. So a framework often contains the structure part of several design patterns. So the architecture style and design patterns describe what, and framework describes how, describes the concrete implementation of perhaps a collection of design patterns. So architecture style design pattern represents a solution to a problem that arises within a particular context when developing software. The context is the situation in which this particular solution applies to. So it's a problem-solution pair in the context. Architecture style design pattern captures the static and dynamic structure and collaboration among key participants in software architectures and designs. So the structure is static. That is like the structure of a house. While the collaboration is dynamic. That is how they pass messages back and forth, how they communicate and collaborate. So participants are the perhaps objects or subsystems. So they are particularly useful for describing how and why to resolve non-functional requirements. That is performance, reliability, dependability, etc. So architecture style and design pattern facilitates reuse of successful software architectures and designs. That is, you had some successful designs before in previous projects, perhaps in the history of software development, many people have many successful experiences. So design patterns and styles are a way to capture the experiences in a formalized form so that future generation programmers, developers can reuse them. So first we'll discuss architecture style, and then we'll discuss design patterns. So architecture style specifies how to organize and connect a set of software components. So it's a pattern of system organization that defines the software architecture of a system. Just like in traditional building architectures, you have different styles. You have the Chinese style, Gothic style, Western style. So software architecture also has styles. So it includes the specification of system decomposition. How do you divide the system up into parts, subsystems, global control flow? Is it based on event passing, message passing, or is it based on threat, procedure control flow, error handling, and intercomponent communication protocols? So here's one very common style, multi-layer. So where you have perhaps a top layer as the user interface, middle layers are the application functions, business logic, and a bottom layer as common services like data storage, database, communication, that is TCP/IP, or HTTP. So each layer communicates only with the layers below it. That is, you can only make calls to components below you in the layer structure. You cannot call up. So each layer has a well-defined API, application programming interface, defining the services it offers, it provides. This can be combined with other styles as well. So the most well-known layered system is the OSI networking layer. If you learn in the networking course, you have a presentation layer, networking layer, link layer, and physical layer. So each layer can issue function calls to the layers below it. So model view controller, this is to separate user interface layer from other parts of the system. So you have 3 parts. The model contains the classes. That is, it encapsulates the data to be viewed and manipulated. The view contains objects used to render the data from the model. That is, display the data. Render means displaying. And also the various controls with which the user can interact. The controls here meaning buttons and dialog boxes. So the controller contains the objects that control and handle the user's interaction with the view and the model. Therefore, there's when the actor, that is the user, issues some events, the controller modifies the model with this arrow, and perhaps and the model upon its change notifies the changes to the view to update the view. So, for example, in Microsoft Excel, you have a multi-view environment. Perhaps you have a table. In addition, you have a graph based on the data in the table. So if you modify the data in the table and you click enter, then the graph is also updated. So this is done via this loop. From the user interface, you modify the underlying model, and the model issues a callback to the view to update the other views. So the benefit of this is to separate the user interface from the data so that you have better encapsulation. So this is somewhat like the boundary control and entity classes separation we saw before. So there's an observer design pattern to separate the model from the view, in the sense that perhaps you have one model and 3 views. So in Excel, perhaps you have one data, underlying data, and you have a table view, you have a bar chart view, you have a pie chart view. And all these are observers of the data. So whenever the data is modified, all the views receive a notification from the data from the model and update itself. So design patterns. So a design pattern is a generic solution, reusable solution to a commonly occurring problem in software design. So it is it's a description or template for how to solve a problem that can be used in many different situations. So it's not the finished design that can be transformed directly into code. That is, it describes at an abstract level the relationships and interactions between objects and classes without specifying the final application classes or objects that are involved. You need to read the description yourself and apply it to your system by really manually, by matching your application to the pattern description. So it typically shows relationships and interactions between classes or objects without specifying the final application classes or objects that are involved. So it makes extensive use of inheritance and delegation. So that is perhaps the design pattern describe relationships between many abstract classes. and then your real application, you are dealing with concrete classes or objects. So perhaps you need to rely on inheritance to make the connection. So design patterns are described using the following main parts. So name and intent, that is the name of the pattern and what it's designed for. Problem and context, what problem is solved under what context, concerns addressed, and abstract description of structure and collaborations in solution, positive and negative consequences of use, implementation guidelines and sample code, and known uses and related patterns. So this is kind of a traditional way of specifying design patterns. Because it's natural language, it's informal, so people have imposed this particular format, 7-point format, to make it more or less uniform in terms of description. So the design pattern descriptions are usually independent of programming languages or implementation details. So because they're meant to be abstract. So here's one pattern. Here's the problem of the bridge pattern. When an abstraction can have several possible implementations, inheritance is usually used to handle this. Say you have a window abstract base class. So remember, italic font indicates abstract base class. And perhaps you have a Microsoft window on Windows and Mac window on Mac OS. So they all have more or less similar behavior. You have, minimize, maximize, and resize, and etc. So, but they're implemented differently. So you can use inheritance to do this, but this binds the implementation to an abstraction permanently, making it difficult to modify, extend, and reuse abstractions and implementations independently. So this is the inheritance hierarchy. Now, suppose you want to develop a new type of window, that is icon window. So regular window is the window you see you can on your Windows system. Icon window is when you minimize a window, it gets turned into an icon on your desktop bar. So it has a different behavior than the regular window, but it has also some common behaviors also. So one way to do this is to have icon window as inheriting from the base class window, because it's different from the regular windows. And then again, you need to inherit from the icon window. You have two platforms, two implementations of icon window. One is a Microsoft window, one is a Mac window. So this is awkward. So every time you add a new type of window, you need to add two children to it, Microsoft and Mac. So we're mixing design and implementation inheritance hierarchies. So really we have two hierarchies here. One is the window, icon window hierarchy. One is the window, MS window, Mac window hierarchy. So window and icon window are the design hierarchies, while the MS window and Mac window are the implementation inheritance hierarchies. So they shouldn't be mixed. So here's the bridge design pattern, so here's the the correct way to do it is to have a abstract base class window, have two child subclasses, icon window and application window. So that is one inheritance hierarchy, and you have a window implementation. And then you have another two subclasses, Microsoft Window Implementation and Mac Window Implementation. So now you have two inheritance hierarchies. They are related via a bridge. So this thing is a bridge. It is a connection, a aggregation relationship between the abstract window and abstract window implementation. Now, these things are concrete. That is, you have icon window and application window, and you have Microsoft Window Implementation and Mac Window Implementation. So their connection is via the bridge. So the window abstract class calls the implementation operations. So, for example, the draw rectangle operation in window, this symbol here is an informal notation for indicating what happens within the draw rectangle operation. So it's calling impl arrow device draw line. So rectangle consists of 4 lines. So perhaps you call draw line 4 times with different parameters, and draw line is defined within the window impl class. So this impl here is perhaps a pointer stored within the window class. So you can refer to its operations with the arrow operator. So, and in the more concrete subclasses, you can add a new operation, draw border, and inherit these old operations from the parent base class, draw rectangle and draw text. So when you call the say draw rectangle, you're really invoking the base class operation, which in turn invokes the window impulse operation, which is in turn redefined depending on if it's a Microsoft window or a Mac window. So you can imagine this call is really flowing up and across the bridge, and then call return gets also up and across gets returned back to the icon window. So that's why it's called a bridge pattern. So a bridge is consists of 2 inheritance hierarchies. One is abstraction, one is implementer. So the abstraction defines abstractions interface, like the window interface, maintains a reference to an object of type implementer, reference meaning a pointer, and so that you can invoke the implementer's operation, real operation, with the pointer arrow syntax within the abstraction operation. And refined abstraction extends the interface defined by abstraction with additional operations like icon window operations. And implementer typically provides only primitive operations, and abstraction provides higher level operations based on the primitives. For example, the implementer can define a draw line operation, while the abstraction, the window, can define a draw rectangle, which is a higher level operation that calls draw line 4 times. And concrete implementer implements the implementer interface and defines its concrete implementation for a particular platform, so Windows or Mac. So the benefit of the bridge design pattern is to separate the 2 inheritance trees. One is the abstraction tree, different types of windows. One is the implementation tree, different platforms, so that you don't have to mix these two in a single inheritance tree. So, any questions? Facade. The problem is to structure a system into subsystems that help reduce complexity. So the design goal is to minimize the communication dependencies between subsystems. So here's one subsystem. If you recall, this little shape like a file folder, this indicates a subsystem. It may contain a bunch of classes, design classes, and there are some other subsystems outside. These are outside classes that communicate with the classes within the subsystem, perhaps by procedure calls. So as you can see, there's a lot of coupling, a lot of dependencies. So the facade pattern essentially imposes a class that provides a single unified interface to a more general facilities of a subsystem, so that everything must go through the facade. So you minimize the coupling. When you change anything within the subsystem, you only need to update the facade. So facade is the word in architecture design, traditional architecture design, where you have a kind of a wall, like a building thing, that sits at the entrance to a compound of other buildings, and from the outside you can only see the facade, you cannot see inside. So that's the idea. So here's the more detailed view, where the facade knows which subsystem classes are responsible for a request and delegates client requests to appropriate subsystem objects. So that is, facade provides a set of public operations like operation A, operation B, but within these operations, it's actually calling the subsystem classes operations internally without telling what the client is doing. So operation A, operation B are wrappers, high-level wrappers for the perhaps many different calls to the internal class operations. So subsystem classes handle work assigned by the facade object having no knowledge of the facade. That is, the calls from the facade to the other classes is always one way. You cannot call from the internal classes to the facade, but only call from the facade to the internal classes. So this is really similar to the when in a class you have public operations and private attributes, right, to achieve data hiding. So this is just bringing it to the architecture level, where you dedicate a class to be the facade, and everything else is internal private. So a proxy design pattern. So sometimes we want to defer the full cost of creating and initializing an object until we actually need it. So for example, in a document editor that can embed graphical objects in a document, objects like large raster images can be expensive to create. So say you have a Microsoft Word document with perhaps thousands of embedded images. Now, these images may take many megabytes of data on the disk. If you bring them into memory upon opening the document, it can take a long time to bring all the data from disk to memory and display the data. So opening a document should be fast. Perhaps you're opening a document, you only need to look at the first few pages. You don't need to bring in all the stuff contained in the document. Perhaps you only bring in enough information to display the first 1 or 2 pages. And when the user scrolls down, then you can bring in additional data from the disk on demand. So we avoid creating expensive objects all at once when the document is opened, because not all objects are visible at any same time anyway. You have a limited window of visibility. So how do you do that with a design pattern? So here's the pattern of proxy. So you have a text document which contains a pointer called image to a image proxy, which in turn contains a pointer to a file, that is the actual image file on disk. So this image proxy acts as a stand-in for the real image. That is, when a document is first opened, you have all these things in memory: document and image proxies. The proxy is small. It's just a small class with a pointer in it, so it's fast to load. So the proxy acts just like the image, instantiates it when needed, and forwards requests to it after creating it. That is, only when you actually make a call to the image proxy and says perhaps display yourself, then image proxy makes a call to the image on disk and pulls the data from disk. But if you never make the call to the proxy to display, then the proxy never pulls the data from disk. So you save a lot of work. So here's the proxy pattern. So the subject is perhaps the image. It's abstract, right? It has italic font, so it means that it's an abstract base class with abstract operation request. And perhaps you have the real subject as the real object that the proxy represents, and a proxy is an abstract. Maintains a reference that lets proxy access real subject. So it provides an interface identical to subjects, so that proxy can be substituted for the real subject, so that anything that calls the subject can also call the proxy, because they offer the same operations. But the proxy plays the trick and controls access to the real subject, and may be responsible for creating and deleting it behind the back of the caller to the subject. So any questions? No? So manage persistent data. So So this is the common problem of you have a volatile memory with the object structure, with perhaps C++ objects with pointers to each other, and you have persistent memory in the table structure. Like in Access, you have student table with a bunch of columns and professor table with a bunch of columns. Well, in the memory, you have student object and professor object pointing to each other with pointers. So now they need to be kept consistent. That is, upon application startup, you need to load up the data from the table structure into the memory object structure, and upon finish, you need to save the information from the object structure to the table structure. There are many issues. How do you map between these two? This mapping is typically straightforward, where each attribute gets mapped into a column in the table. Object IDs. So in object-oriented programming, each object in memory typically has a unique identifier, but in the relational database table, there's no identifiers, there's no IDs. So you need to create and assign the IDs when you bring data from the database into memory. So it's required by the old programming language. Inheritance is typically not supported in the relational database. So, but it is in the supported in the object-oriented programming language. So, how do you transform this inheritance relationship into something that can be supported in the relational database? This is typically done with associations between the different tables. Data type mismatches. So programming languages often define different types, more rich types than database types. So you may have a double floating point integer short. Well, in the database, typically there's just strings or integers. There's so you need to map between these two different type systems. And operations. How do you store operations in the DBMS? You can't, right? So you can only store attributes of classes. But fortunately, because these classes are typically entity classes that are typically have very simple operations like get and set. So these you don't need to store the operations. So the goal is to encapsulate database access to hide its implementation details from the application, to hide this mismatch between these two formats with the intermediate layer. So the first approach, brute force, is when you embed SQL in application classes like JDBC or ODBC, Open Database. I forgot the abbreviation. So these are APIs that you can use to formulate SQL queries within C++ or Java. So this is a direct access of database with SQL queries. So the approach is you have a customer class at runtime as an object. So you build select statement, issue the select statement to the database as a string, and get a result set back, and set data values within the main memory objects. based on the data from the database. So you can write code very quickly. It's okay for small applications and for prototyping, but the application classes are coupled directly to the database schema, so schema changes require reworking the application code. So whenever you change the database schema by perhaps adding a column and deleting a column or renaming a column, you need to go in and modify your application code in the build select statement. You need to reflect the change in the schema. So it's not very it's not good encapsulation. So not an encapsulation strategy. So you can use data access objects where you impose an intermediate layer between the application and database, and application objects can make calls to the data classes, that is Java data object or ActiveX data object. And so the application objects do not directly formulate SQL queries. They formulate higher level queries, like get a particular attribute to the data access object, and they in turn issue the select query and get the results back and parse it and return it in the appropriate format to the application objects. So here's the sequence diagram. You have a customer object as before. Now you impose a additional layer, customer data object, and the customer issues a read customer, perhaps passing in as parameter the customer ID, and so get key values. And so customer data object issues a call to get the key values. That is, what keys are there in the customer object? What attributes are there? And then it uses the select SQL statement, gets results from the database, and set data values. So based on the keys. So perhaps the key is employee ID, and the data value is 21345. So this approach encapsulates the source code that handles the data access in one place. That is within the customer data class. However, it needs recompilation of data classes when changes are made to the database. So every time you modify the database schema, you need to recompile this class, customer data class. So this is better than the previous one because the customer class does not have to be changed. You need to change these data access objects, which are typically simpler and smaller in number than the application objects. So this is progress. This is better encapsulation. So another approach is to have a persistence framework, persistence layer that maps objects to the database so that simple changes to the database schema do not affect the object code. So now you have a persistence framework and mapping classes. So the persistence framework is similar to the data classes before, data objects we saw in the last slide. But you have intermediate mapping classes to map the object attributes to the database tables. So the persistence framework calls getMaps from the mapping classes and builds select statement and issues the SQL select statement to the database and set data values. So the pro is that application classes do not need to know anything about the database schema. They do not even know that a database is being used. So impacts performance because you have the additional layer of mapping classes in between. So notice the difference between this one and the previous one. In the previous one, you had a one layer customer data, and this customer data must have knowledge of the database schema to build the SQL select statement. While here, you have additional mapping classes, so the persistence framework first does a get maps to get the corresponding columns and tables from the attributes and objects, and then it builds the select statement. Therefore, the persistent framework doesn't have to know the database schema. If the database schema changes, you need to change the mapping classes. Say professor is changed to instructor, it's a change of name, then the mapping class needs to change the mapping, so the persistence framework doesn't have to change its code. So of course, the more layers you have, the more overhead you have. So it impacts performance. So I think we're at the end of the design chapter. No, we're not. We have class design. So that is how to design internal details of design classes. So now we're coming to this part. That is design class. So it's a little bit awkward. When I say design, sometimes I mean it as a verb, as designing something. Sometimes I mean it as a adjective, as design class versus analysis class. So you're designing the design class and design subsystem and interfaces. So remember in the analysis chapter we discussed use case realization dash analysis. Now we're doing use case realization dash design. So identifying the participating design classes for each use case from the analysis classes that participate in the use case. So you often derive multiple design classes from a single analysis class. In addition, perhaps you need to add additional classes to handle special requirements of the use case to achieve design goals like dependability, reliability, etc. And perhaps add additional classes needed to implement the use case, to deal with the implementation environments like middleware and operating systems. You should preserve traceability. That is, you should be able to trace between the use case in the requirements document and use case realization dash analysis in the system analysis document, and finally to use case realization dash design to the design document. So you should be able to point to a design class and say, this guy is for that use case, and the corresponding analysis class is this. So, and also backwards. So you should specify the class diagrams dash design that shows the participating design classes and implementation requirements that collect the non-functional requirements that will be handled during implementation. So So a design class is a class whose specifications should be specification, not plural, so it's a typo, has been completed to such a degree that it can be implemented. This is as opposed to analysis class, which is abstract, which only addresses the functional application requirements and is oblivious of the implementation environment. But now we need to consider the dirty details. We need to implement the problem domain, that is the analysis model classes using solution domain, that is implementation technology classes. So boundary class in the analysis class, implementation is determined by the use of specific UI technologies. So in ASP.NET, you use design classes stereotypes as web forms. So remember, this double bracket indicates a stereotype that you can place as annotations to a class to indicate a special class. Of course, in other implementation technologies, for example, in Java, you have different design classes for implementing a boundary class. And also, a boundary class can be turned into dozens or hundreds of these design classes. So entity class implementation is determined by the use of data management technologies. So if you're using a relational database like what you're doing now with Access, then the design classes encapsulate a relational database. Control class implementation is determined by issues related to distribution. That is, do we need a separate design class at each node? So if the system is distributed at different locations, and the different locations need to communicate and cooperate, then perhaps you need to duplicate your design class at different nodes in the system, and they should synchronize with each other. Performance, do we need to merge boundary entity classes? Now, as the control class, sometimes you can merge it with the boundary class or the entity class to reduce overhead. Remember, the more layers you have, the more overhead you have. So to improve performance, perhaps you need to sacrifice some modularity by merging the classes. Transactions, do we need transaction management? That is, a transaction is a collection of operations that must be finished atomically as a whole, or none of them must be finished. So database transactions is one type of transaction. You can also have application level transactions, where you have a group of application level operations that need to be atomic. So if you need transaction management, then perhaps you need to design control classes to encapsulate that. And within the control class, you do the atomic operation. If any one fails, you roll back everything. So you should preserve traceability to analysis classes. That is, each one of the boundary control and entity classes may be turned into several or many design classes, and you should be able to trace back and forth between the analysis classes and design classes. So class design, so how do you identify the design classes? So select reusable components using class libraries and generic design mechanisms. We discussed the design mechanisms a little while before. One is the database mechanism with data access objects, or with the persistence framework, right? That is a mechanism that you can select as reusable components into your system, so you don't have to write it from scratch. Or you can have class libraries available that you can use. Complete the specification by adding attributes, associations, operations, types, visibility, that is public, private, protected, and other constraints. So active classes have their own thread of control. That is, typically classes are passive. That is, the object sits there and waits for some other thread, some other classes to call it. If no one calls it, it sits there idle. It's waiting for a call. But active classes are active. That is, it has its own thread within it. It can make calls, initiate calls to other classes. So active class is usually a boundary or control class, and is shown with a thicker border in the class diagram. Can be identified by considering performance, throughput, and availability requirements of different actors. So if you need a fast real-time response, it perhaps can be managed by a dedicated active object for taking input and providing output with its own thread. Or system distribution onto nodes. Perhaps you can place one active object per node, and so that they can manage the communication between the nodes. Or perhaps for handling other requirements like system startup and termination, deadlock avoidance, starvation avoidance, reconfiguration. So perhaps you dedicate an active object to monitor the activity in the system. And when something happens, like a deadlock occurs, you can abort something to get out of the deadlock. So these are the possible reasons, the three of these, for needing and using an active class, an active object. And the third step is to restructure the design model by adding associations between the classes and increasing reuse by inheritance. So perhaps by pulling out some common parts into a base class to reduce the clutter and increase reuse. And optimize the design model by revising access paths, which means that if class A needs to communicate with class B a lot, then, and you have, perhaps you need to have 5 hops between them. So you need to class A to class C, and then class D, and then to class B. So it may have a lot of overhead. Then perhaps you need to add a direct access path between class A and class B by adding an association between them to optimize performance. Collapse classes, that is, if you have too many classes, it introduces too much overhead at runtime. So perhaps you can collapse some into more coarse-grained classes to reduce inter-object communication and to improve performance. obviously, calling your local operation within the object is much faster than issuing a message and calling another object's operations. Caching or delaying expensive computations. That is, if you have expensive computation, perhaps when you calculate it once, you can store it and cache it. And next time when you call the operation, you can just return the cache instead of making the computation again. Or you can delay it. That is like the proxy design pattern we saw before. You can load up a proxy to represent the expensive load image operation, so that when you actually use the object, then you call the proxy and load it from disk. Otherwise, you leave it on the disk. So describe design classes using the syntax of programming languages. So this is, again, different from the analysis classes, where you can use pretty much any convenient syntax you want. Like you can say something is attribute is money attribute, but now you need to actually say this money attribute is really a type of double or integer in the syntax of the language you use. So the reason is that you need to prepare it for implementation later. So well-formed classes should have high cohesion and low coupling. We saw this before with package design. So now we see this again. So a class should model a single abstract concept and should have operations that support the intent of the class. And low coupling means that the class should be associated with just enough other classes to allow it to realize its responsibilities. And the class should do what users of the class expect, not more and no more and no less. So if you have a bank account class, it should withdraw and deposit. It shouldn't do anything less than that. It shouldn't do anything more than that. So you shouldn't, do a login operation on a bank account class. That doesn't make sense. So a class should make available the simplest and smallest set of operations possible. So so there shouldn't be multiple ways of doing the same thing. So this is to simplify the use of the class, of the user of the class as other classes that may call to the class. If you have a set of well-designed primitive operations, then it's easier to use. Okay, I think we'll stop here. So this example I'll discuss next time. Okay. So your activity, is it 2 or? Yeah, 2 is due. So as you saw before, right, you need 2 copies. One is for peer review, one is for me to grade. So this is just for you to see what other people are doing yourself.